Hello students, hope in these trying times of COVID, you're all safe and healthy. I'm Dr. Seema Singh and you're watching my channel Bonding with Chemistry. Before I take up today's video, I would like to extend my heartfelt gratitude to all you viewers who helped me reach another milestone on YouTube, hitting the mark of over 1000 subscribers. A big thank you to each and every subscriber of my first 1000 club. You will all be always special. Let us now continue with part 9 of chapter 3, Metals and Nonmetals. In today's video, we will learn how metals react with nonmetals to form ionic compounds. Here is a list of topics that I've already covered in my previous videos. You can find the links to these topics in the description box below. In my upcoming video, we will study the properties of ionic compounds. So don't forget to subscribe to my channel and do press the bell icon for receiving the latest notifications. Before we study how metals and nonmetals react with each other to form ionic compounds, let us understand why metals and nonmetals react in the first place. For this, we will brush up few simple or basic concepts that we have learned in class 9. We will also touch upon few topics that we will study in greater detail in the next chapter, carbon and its compounds. Let us begin with brushing our knowledge about electronic configuration, which is also known as electronic structure. Electronic configuration in simple terms is the arrangement of electrons or distribution of electrons around the atomic nucleus. That is, it describes where the electrons are located around the nucleus of an atom. For ease of writing, I am abbreviating electronic configuration as EC. Now for writing the electronic configuration, we need to remember certain points. First of all, in an atom, the nucleus comprising of proton and neutron is present in the center and the negatively charged electrons move around the positively charged nucleus in fixed paths known as the energy level or the energy shells. These energy shell or level are denoted by numbers 1, 2, 3, 4 or alphabetically known as K, L, M, N respectively. That means K shell is equivalent to 1, L is equivalent to 2, M 3 and so on. So if I have these shells around the nucleus, the first one closest to the nucleus is denoted by K alphabetically, or you can denote by number 1. The next one is known as L, which is equal to 2. The third one is known as M, which is equal to 3. And this one is N, which is equal to 4 and so on. Well, why they are so called, you will be studying in your higher classes when you learn more about quantum numbers. Now, as you can see in this figure, these shells are represented by circles around the nucleus with the first shell or K shell closest to the nucleus, followed by 2, 3, 4 or L, M, N respectively, which I've already explained. Well, this model of atom is known as the Bohr's model of atom. The energy of these shells increases as we move away from the nucleus. That means your K shell here has the lowest energy, whereas N has the highest or maximum energy. The next step is filling electrons in these shells. For that, first of all, we need to know the number of electrons in an atom, which is equal to its atomic number represented or denoted by Z. For example, let's say atom carbon. Atomic number of carbon, which is represented by Z, is equal to 6. Therefore, the number of electrons in carbon is equal to 6. The next point is to know maximum number of electrons that can be accommodated in any energy level. How do we know this? This is given by a scheme known as Bohr-Bury Scheme. Now, Bohr and Bury are the name of two chemists, Niels Bohr and Charles Bury. According to this scheme, the maximum number of electrons that can be accommodated in any given shell is given by the formula 2n square. Now what is n out here? N is the shell number. I told you for K n is equal to 1, for L it is 2 and so on. So the maximum number of electrons that can be accommodated in K shell will be 2 into 1 square, which is equal to 2. Let us say for M, it is going to be 2 into 3 square, which is equal to 18, and so on. So looking at this table, I can say K, which is N equal to 1, can have maximum electron 2, and L, M, N can have 8, 18, 32 electrons respectively. Now you need to remember an important point, that the outermost shell, which is also known as the valence shell, cannot accommodate more than 8 electrons, even if it has capacity to accommodate more. Now what does that mean? Let me explain with an example. If I say M shell, right, you have a nucleus and you have K, L and M shell, and M happens to be the outermost shell. Now this outermost shell, which is also called as the valence shell, cannot have more than 8 electrons, even though the maximum rated capacity for M is equal to 18. So this M cannot have more than 8 electrons if it happens to be the valence shell or the outermost shell. This is because the moment outermost shell has 8 electrons, the atom becomes highly stable. We'll learn more about this in higher classes. Here to students, there is a catch or an exception. If your outermost shell, which is also known as the valence shell, happens to be the first energy level. Now, which is the first energy level? K. Then it cannot have maximum 8 electrons. It can have maximum 2 electrons. Now, why this is so? Because according to Bohr-Bury scheme, if K is equal to 1, it can have only maximum 2 electrons. Also, we're going to learn further that if your valence shell, which happens to be the first shell, has 2 electrons, it makes the atom very stable. Let me explain this point with the help of an example again. Suppose we have element helium. The atomic number for helium is 2. So if I have to write its electronic configuration according to Bohr-Bury scheme, I'll say electronic configuration for helium is equal to, let me write the shells like this. Since it has 2 electrons and K can have maximum 2 electrons, I put 2 here. Now 2 electrons in the valence shell, which also happens to be the first energy level, makes helium quite stable, that means unreactive. But suppose we have another element, lithium. Its atomic number is 3, so the electronic configuration for lithium can be written as, again here I'll put up KLM shell. Now it is 3 electrons. So I'm not going to put up more than 2 electrons in the first shell because that will be violation of your Bohr-Bury scheme. Now if you look at the point, the outermost shell cannot have more than 8 electrons. So you might have a point in mind that still lithium has 1 electron. So instead of 2, we can put here 3. No, my dear students, this is incorrect because this is violation of Bohr-Bury scheme. The first shell or the first energy level can have only 2 electrons. And if this first shell happens to be the valence shell, as in the case of helium, you have helium here, you have 2 electrons in K shell, which is not only the first energy level but also the valence shell. It makes the atom quite stable and hence unreactive. So for lithium, we'll write down 2 and in the next shell, we'll write down 1. So here L is the valence shell and the number of electrons in the valence shell, 1, is known as valence electron. So you have 1 valence electron in case of lithium and 2 valence electron in case of helium. Another point you need to keep in mind while writing the electronic configuration is that electrons do not occupy the higher energy level until and unless all the inner shells are completely filled. Now you might find these two rules contradictory as far as your current class level is concerned. But as you move ahead in higher classes, you will understand the reason for this. So keeping all these points in mind, let us start writing the electronic configuration of few metals, non-metals and noble gases. We will stick to only those elements with which you are familiar or which are as per your class level. We will not be showing the Bohr's model for writing electronic configuration, but a simpler way as illustrated by the examples which I'm going to take in a short while. We will begin with writing the electronic configuration for noble gas elements. As you've already learned that the elements which are categorized as noble gases, namely helium, neon, argon, krypton, xenon, and radioactive radon, are quite unreactive. They are extremely stable and therefore do not tend to form chemical bonds and have little tendency to gain, lose, or share electrons. You will study in higher classes that xenon does react to form compounds with fluorine and oxygen. Dear students, we'll only consider the electronic configuration of the first three noble gases, that is helium, neon, and argon. Rest will leave for higher classes. So beginning with helium, although we've already done its electronic configuration, but let us quickly recall. Z, or the atomic number for helium, is 2, and therefore number of electron which is equal to atomic number is equal to 2. So for writing the electronic configuration of helium, we write down the shell designations as K, L, M, N. Since helium has only 2 electrons and your K shell can accommodate maximum 2 electrons, so we write 2 here. Here, since rest of the shells are empty, you can skip writing them or representing them. So I can say the electronic configuration of helium is equal to 2. Moving to the next one, neon. The atomic number of neon is 10 and therefore number of electrons is also equal to 10. Coming on to the electronic configuration for neon is equal to, you already have K, L, M, N. You will have 2 electrons in K shell. Your L shell can have maximum 8 electrons. So 2 have already been accommodated in K shell. Remaining 10 minus 2, 8 electrons will move on to L shell. The next noble gas element is argon, which has atomic number of 18 and therefore number of electrons is equal to 18. So the electronic configuration will be written as 2 in K shell. L shell can have maximum 8 electrons. M shell can have maximum 2 into n square, that is 2 into 3 square, 18 electrons. Now we have 10 electrons already accommodated. The remaining 8 electrons move on to shell M. So the electronic configuration of argon is written as 288. So the electronic configuration of helium, neon and argon can be represented as helium is equal to 2, neon is equal to 2. You're going to use or separate the two shells by comma, 2, 8, and for argon it is 2, 8, 8. Here commas are used to segregate the shell. So you have a choice. If you want, you can mention here K, L, M, N, or you may skip. You can simply write helium is equal to 2, neon 2, 8 and argon 2, 8, 8. Let us now move on to writing the electronic configuration for few metals. Beginning with sodium. Remember students, for writing the electronic configuration, the first thing you need to know is the atomic number. If in case you falter with the atomic number, automatically your electronic configuration will go wrong. So beginning with sodium, the atomic number for sodium is 11. Right? So the number of electron is equal to 11 here. Thus the electronic configuration can be written as 2, 8, 1. Let me mention the shell numbers K, L, M. Moving on to the next, magnesium. Magnesium has atomic number 12, so number of electrons is equal to 12. So you have electronic configuration 2, 8, 2. Coming on to aluminium, we have aluminium atomic number 13, so number of electrons is equal to 13. The configuration is 2, 8, 3. Moving on to potassium. Potassium has atomic number 19. Be a little careful while writing the electronic configuration of potassium. Just see here, number of electrons is equal to 19. So the electronic configuration is 2, 8, right? So we have 8 plus 2, 10 electrons already accommodated. 19 minus 10, we have 9 electrons. So if I mention the shell numbers here, K, L, M, your M shell can accommodate 2 into 3 square, that is equal to 18 electrons. So we have 9 spare electrons to be accommodated. I might write 2, 8 comma 9 because M shell can have maximum 18 electrons. But the moment I do this, I am violating the next rule which says that the outermost shell cannot have more than 8 electrons. So although M shell can accommodate 18 maximum electron, but since here it is the outermost shell or the valence shell, it cannot have more than 8 electrons. So this electronic configuration for potassium is incorrect. So the correct configuration for potassium is 2, 8, 8. We are going to shift one electron to the next level or the higher energy level, that is your N shell. So the electronic configuration for potassium becomes 2, 8, 8, 1, where N is now your valence shell and the number of valence electron for potassium is 1. Similarly, we can write down the electronic configuration for calcium, which has atomic number equal to 20. Therefore, number of electrons in calcium are equal to 20. Again, the electronic configuration, if we go by the similar pattern as potassium, I'm going to write here 2, 8, 20 minus 10. We have 10 electrons pair. I can put it in M shell because M can have maximum 18 electrons. But the moment I do this, I'm violating the rule that the valence shell, which is right now M shell, cannot have more than 8 electrons. Therefore, this is incorrect configuration and the correct configuration for calcium is 2, 8, 8. The remaining 2 electrons I'm going to push to higher energy level, that is your N shell. So the electronic configuration for calcium is 2, 8, 8, 2 and we speak that as 2882. Let us now move ahead and write down the electronic configuration for few non-metals. Nitrogen. Nitrogen has atomic number 7, therefore number of electron is equal to 7. Your configuration for nitrogen is going to be 2, 5 or 2, 5. For oxygen, the atomic number is 8, number of electrons are equal to 8 here. So you have the electronic configuration as 2, 6. Coming on to fluorine, which is having atomic number 9. So number of electrons are equal to 9. You have the electronic configuration as 2, 7. Moving on to phosphorus. Phosphorus, the atomic number is 15. So the number of electrons for phosphorus are 15. You have 2, 8, 5. Let me designate the shells as KLM. Finally, we have chlorine. For chlorine, the atomic number is 17. Number of electron equal to 17 and the electronic configuration becomes equal to 2, 8, 7. 2, 8, 7 is the electronic configuration of chlorine. Now when we have become familiar with writing electronic configuration for metals, non-metals and noble gases, let us come back to our question. Why do metals and non-metals react? Now this is something to do with electronic configuration and we are going to consider the electronic configuration of noble gases. Why noble gases? Because we just learned that noble gases are quite unreactive and stable and you all know that everything in this universe looks for or seeks stability. Now if we look at the electronic configuration of neon and argon, we see that their valence shell L and M respectively have 8 electrons. And when you will learn about the electronic configuration of the remaining noble gases, namely your krypton, xenon and radon, you will see there also their last shell or the outermost shell has 8 electrons. Helium is an exception. Here its outermost shell, which happens to be the first energy level, has 2 electrons. Right? Now because these noble gases have 8 electrons in the valence shell except helium, these gases are said to be stable. So having 8 electrons in the valence shell is what makes them stable and unreactive. Helium is an exception here. We've already spoken about it. It has 2 valence electrons. So if I ask you what makes noble gas element so stable, the answer is having 8 electrons in the valence shell is what makes them stable and unreactive. And here by stable we mean that their valence electron do not participate in chemical reactions. Now if you look at the electronic configuration of metals and non-metals that are listed here, we see that neither the atoms of metals nor that of non-metals have stable configuration like that of noble gases, which means they do not have 8 electrons in their valence shell. Look here, sodium has 1 electron, valence electron, magnesium 2, aluminium 3. Again, potassium has 1, whereas calcium has 2 valence electrons. None of them have 8 valence electron in the outermost shell. Now here you might say magnesium, just like helium, has 2 electrons in its valence shell. Then why is magnesium so reactive whereas helium is quite unreactive? My dear students, you need to remember your valence shell has to be your first shell in order to achieve stability. In case of helium, the valence shell is the first shell, whereas in case of magnesium, the valence shell, which happens to be M shell, is the third shell, and hence magnesium is so reactive. Looking at the electronic configuration of nonmetals, we see here nitrogen has 5 valence electron, whereas oxygen has 6. Fluorine has 7, phosphorus, sulfur, and chlorine have 5, 6, and 7 valence electrons respectively. Thus, neither metals nor nonmetals have 8 electrons in their valence shells, but they have a strong desire to achieve the same, as everything I told you in the universe looks for or seeks stability. Thus, atoms of various elements such as metals and nonmetals combine with one another to form compounds so as to achieve the nearest noble gas configuration with 8 electrons in their valence shell and thus become more stable. This is known as the octet rule, having 8 electrons in an atom's valence shell, except helium, which has 2 valence electrons, and here the rule is known as the duplet rule. And how is this octet obtained? This octet an atom can achieve by losing or gaining or sharing its valence electrons. In this video, we'll only concentrate on losing and gaining aspect of valence electrons. The sharing part will take up in the next chapter, carbon and its compounds. There are indeed exceptions to octet rule, which are currently above your class level. So to summarize, if I ask why do metals and nonmetals react, the answer is they react in order to obtain stable octet configuration, except hydrogen and lithium, which react to achieve a duplet configuration similar to that of helium. Now when we know the answer why metals and nonmetals react, let us find out how they achieve or attain the stable octet configuration. Well, in order to have their octet complete, metals which generally have 1 to 3 electrons in the valence shell lose electrons. Once they lose electrons, they become positively charged ions, which are also called as the cations. Thus we say metals are electropositive in nature. Remember that the charge on the cation is equal to the number of electrons lost by the metal. Let me explain this with an example. Let us say metals in general be denoted as M. Now metals have tendency to lose electrons and convert into positively charged ions if the number of electrons they lose is equal to N. So the charge on this metal will be equal to N positive. Taking examples, consider sodium. Sodium has atomic number 11 and its electronic configuration is 281. Now if you look carefully, if sodium loses this electron, the valence electron, L will become the valence shell once this one electron is lost. And now this L shell has its octet complete, so sodium cation will become stable. So I can write here Na. If it loses its one valence electron, it converts into Na with one positive charge. Why? Because it has lost one electron. And it is not important to show the loss of one electron. It is understood if I write a positive charge on a metal, say M. It means here the number of electron lost is equal to 1. Let us take one more example, say aluminium. Now aluminium has 3 valence electrons. If it loses 3 electrons, the next shell, that is the L shell, becomes the valence shell and its octet is complete. So aluminium with 283 configuration has a tendency to lose 3 electrons, and therefore you have aluminium 3 plus cation with electronic configuration 28. Now since this cation has octet complete, it is a stable cation. Let us now see how nonmetals achieve octet configuration. Nonmetals that have 5 to 7 electrons in the valence shell attain octet configuration by gaining electrons. See, it is very difficult to lose 5, 6 or 7 electrons. Here energy consideration are there which you're going to study in subsequent chapter. And when they gain electrons, the negative charge will increase. They form negatively charged ions which are known as anions. And hence nonmetals are electronegative in nature. Now here the charge on the anion is equal to the number of electrons gained by the nonmetal. In case of metals, the number of electrons lost by the metals decide the charge on the cation. Here it is the number of electrons gained by the nonmetal. My dear students, note that nonmetals generally have 4 to 8 electrons in their valence shell. We are considering nonmetals with 5 to 7 valence electrons because if valence electrons are 4, for example the case of carbon, the electronic configuration for carbon is 2, 4. Then it is difficult for this nonmetal to gain 4 electrons. It doesn't gain or lose 4 electrons. It shares. And we said that sharing of electrons we are going to study in the next chapter, carbon and its compounds. And if nonmetals have 8 electrons, those nonmetals are called as the noble gas elements. You know that they're already stable. They have their octet complete. Let us look at some examples to understand these points, beginning with nitrogen. Nitrogen has atomic number 7. The electronic configuration is 2, 5. Now it is difficult for nitrogen to lose 5 electrons. It wants its valence shell to have 8 electrons. So it gains 3 electrons. So when nitrogen with electronic configuration 2, 5 will gain 3 electrons, it will develop 3 negative charge. And this ion is known as nitrogen anion, or it is also known as the nitride ion. Taking one more example, say chlorine. Chlorine has 7 electrons in its valence shell. It just needs 1 electron. So chlorine with electronic configuration 287 accepts 1 electron to form Cl negative, which is known as chloride ion. Now it has configuration 288. In case of nitride, you have the configuration 28. Now let us move further to study the most important topic from this video. That is how metals react with nonmetals and form ionic compounds. My dear students, we just learned that metals have tendency to lose valence electrons so as to achieve stable electronic configuration. Now if a metal wants to lose electron, there has to be some acceptor for these electrons, isn't it? And that acceptor, my dear children, is a non-metal. I mean, you want to donate say few old clothes or books or a pen. Shouldn't there be some takers for it? If there are no takers, there are no donors. So it is basically a give and take relationship between metals and non-metals. Metals donate 1 to 3 electrons in order to obtain nearest noble gas configuration, and these electrons are accepted by non-metals, which too are able to complete their octet by this process. Let us understand this with the help of an example, say formation of sodium chloride. Now first of all, you should know the chemical formula of this compound, sodium chloride. It is made up of sodium and chlorine. So the formula of sodium chloride is NaCl. The next thing you need to identify is the metal and the non-metal. Here sodium is the metal and chlorine is the non-metal. So sodium is going to lose electron and these electrons are going to be picked up by chlorine. So we say chlorine is going to gain electron. Once we have identified the metal and the non-metal, we need to write their respective electron dot structures. Before moving ahead, I'll quickly help you learn how to write these structures for simple elements. The details of electron dot structures, also known as the Lewis structures or Lewis dot diagrams or Lewis electron dot structures after the name of the scientist who introduced it, will be taken up in the next chapter, carbon and its compound. It is an important topic and therefore needs a dedicated video. For writing Lewis structures, the elements are represented by their symbols and the valence electrons are represented by dots around the symbol. Sometimes both dots and crosses are used, but we will stick to using only dots. Let us understand this with the help of few examples. Suppose I have to write down the electron dot structure for hydrogen. Okay. So first of all, I should know the symbol for hydrogen, which is H. So this is the symbol of the element. Look here, this one. Represent the valence electron with the help of dots. Hydrogen has atomic number 1. Number of electron is equal to 1. Its electronic configuration is 1. So it has 1 valence electron. Now this valence electron has to be shown by a dot around the symbol of the element. Let us take the example of carbon. Carbon has atomic number 6, fine, and its electronic configuration is 2, 4. So its electron dot structure will be represented as the symbol C. Now 4 valence electron. You can't write 4 valence electron like this. There is a systematic way of writing it. First of all, you're supposed to distribute single electron on each of its 4 sides like this. 1, 2, 3, 4. Now if you have more valence electron, you will start pairing. You will start showing 2 electrons. Let me give you an example. Say oxygen. Oxygen configuration is 2, 6. So you're going to write the symbol O. 4 electrons in 4 directions and then start pairing. The 5th electron here, you see the pair here, and 6th electron here. If you look at chlorine, which has electronic configuration 287, the electron dot structure will be represented as Cl, 7 electrons, 1, 2, 3, 4. Now start pairing, 5, 6, 7. Let me take one more example. Say for argon, 2, 8, 8 is the electronic configuration. So the symbol Ar, 1, 2, 3, 4. Start pairing, 5, 6, 7 and 8. I've taken all non-metals. Let me take example of few metals. Say calcium. Calcium atomic number is 20. 2, 8, 8, 2 is the electronic configuration. 2 the number of valence electrons. So the symbol and 1 and 2 valence electrons. Let us come back to the formation of sodium chloride. Well, these are the electron dot structures for sodium and chlorine. Sodium has 1 valence electron. If it loses this electron, it will attain the noble gas configuration of that of neon 2, 8. That means Z is equal to 10. And 10 is the atomic number for nearest noble gas, which is neon. Similarly, if we look at the valence electron of chlorine, here 7. If chlorine gets 1 electron, it will have a configuration of 288, which is equal to 18 electrons, and 18 electrons means atomic number that of argon. So both sodium and chlorine can achieve octet configuration by losing and gaining electrons respectively. And how many electrons they have to actually lose or gain? Sodium has to lose 1 electron, whereas chlorine needs to gain 1 electron or accept 1 electron. So sodium donates its 1 electron to chlorine. Sodium loses electron and chlorine gains electron. And in this process, sodium obtains octet configuration, whereas chlorine also obtains its octet configuration. So I can write it, when Na and Cl are going to combine, you will have Na. After losing an electron, it will have a positive charge, whereas chlorine, after gaining 1 electron, will have its octet complete and a negative charge. Now opposite charge attracts. These oppositely charged ions are attracted and drawn closer to each other due to electrostatic force of attraction. Thus, a bond is created or formed between Na positive and Cl negative, and that bond is known as the ionic bond or the electrovalent bond. We can define ionic bond as a type of chemical bond that involves the electrostatic force of attraction between oppositely charged ions. And the compounds that are held together by ionic bonds are known as ionic compounds or electrovalent compounds. Here, my dear students, you need to remember that during the formation of ionic bonds, exchange of only valence electrons take place. The electrons of remaining inner shells do not participate in the bond formation. Also remember, you need to have a metal and a non-metal to form electrovalent or ionic bond. It cannot be formed between two metals or it cannot be formed between two non-metals. Thus, this is the formation of NaCl. Now, if I ask you an opposite question, what are the ions present in sodium chloride? Will you be able to do it? It's very simple. First, you need to identify the metal and the non-metal. I've already explained that to you earlier. Remember, in an ionic compound, the metal is written first, followed by the non-metal. So, sodium is the metal, chlorine is the non-metal, and a metal will have positive charge. and a non-metal will have negative charge. How much will be the positive and negative charge? You need to find that out by knowing the electronic configuration. Sodium has 281, chlorine has 287 configuration. Sodium has to lose one electron, so the charge is 1 positive. You need not show 1. And chlorine needs to gain 1 electron, so it has a uni-negative charge, right? So the corresponding ions in sodium chloride compound are Na positive and Cl negative. Let us consider some more examples illustrating ionic bonds. Say formation of magnesium oxide. First of all, you need to know the formula of magnesium oxide, MgO. Magnesium is the metal, oxygen is the non-metal here. So, writing the electron dot structure for magnesium, which has a configuration of 282 because its atomic number is 12. Magnesium has 2 electrons in the outermost shell. For non-metal oxygen, whose electronic configuration is 2,6, it has 6 valence electrons, so 1, 2, 3, 4, start pairing 5 and 6. Now magnesium needs to lose 2 electrons, whereas oxygen is in need of 2 electrons. So magnesium gives or donates its 2 electron to oxygen, which readily accepts. Once magnesium donates electron and oxygen accepts electron, you will have Mg with 2 positive charge because it has lost 2 electron, and oxygen has gained 2 electrons and therefore will have 2 negative charge. Now opposite charge are going to attract each other, they are going to come together by electrostatic force of attraction, and thus you have magnesium oxide as the ionic compound formed. Let us take one more example. Formation of magnesium chloride. The formula for magnesium chloride is MgCl2. Here magnesium is the metal, chlorine is the non-metal, but remember you have 2 chlorine atoms. Let me explain why. Writing the electron dot structure for magnesium, Mg282, it has 2 valence electrons and therefore I am writing 2 dots. Coming on to chlorine, chlorine has a configuration of 287. It has 7 valence electrons, 1, 2, 3, 4, start pairing 5, 6, 7. Now magnesium has 2 electrons to lose, whereas chlorine requires only 1 electron. So what do? We'll take another chlorine atom. Same configuration here also. So now 1 electron magnesium is going to donate to this chlorine atom, and the second electron it is going to donate to this chlorine atom. So when magnesium donates electron to 2 chlorine atom, you will have magnesium cation with 2 positive charge, and you will have chlorine anion with a negative charge, but they are going to be 2 chlorine anion or 2 chloride ion, and thus the formation of MgCl2 is shown or represented or explained. Let us move ahead. In this table, I have provided the structure of some common ionic compounds. As far as your NCERT is concerned, you have the following 4 ionic compounds in your syllabus. You should know the formation of these 4 compounds. But I'm sure after understanding the fundamentals, you are in a position to show the formation of some common ionic compounds as these. Let us quickly summarize few characteristic features of ionic or electrovalent bond. Remember, metals always lose their valence electrons to form cations, positively charged ions, whereas non-metals are going to always gain electrons to form negatively charged ions known as anions. The number of positive and negative charges on a metal and non-metal will be equal to the number of electrons they lose or gain respectively. Also, the number of electrons which an atom lose or gain during the formation of ionic bond is known as its valency or electrovalency. Let me explain this. Sodium with electronic configuration 281, it loses 1 electron and therefore its valency or electrovalency is +1. Aluminium has a configuration of 283, it loses 3 electrons and therefore its electrovalency is 3. Coming on to non-metals, oxygen configuration 2,6, it gains 2 electrons and therefore the electrovalency is -2 or -2. Sometimes you can also write 2 negative. Both are acceptable. Coming on to chlorine, chlorine has an electronic configuration of 287. It accepts one electron and therefore has an electrovalency of 1 minus or negative 1. And why are ionic bonds formed? They are formed due to electrostatic forces of attraction between oppositely charged ions. That means attraction between cations and anions. Let us finally put to test what we have learned by answering a simple question. The question says, write the electron dot structures for sodium, oxygen and magnesium. Although I've covered up in my explanation part, let me do this quickly for you. Answer 1. Sodium. The electron dot structure is, it has configuration 281. So its electron dot structure is represented by Na with 1 valence electron, represented as dot. Coming on to oxygen, its configuration is 2, 6. So its electron dot structure is 1, 2, 3, 4. Start pairing 5 and 6. Next is magnesium. Its configuration is 282. So electron dot structure is Mg, represented by 2 dots for its 2 valence electrons. The second part is show the formation of sodium oxide and magnesium oxide by the transfer of electrons. My dear students, you can see the formation of these two compounds in the table that I have provided here. Coming on to the last part, what are the ions present in these compounds? So when you are going to show the formation of sodium oxide and magnesium oxide, you automatically will know which ions are present. But for ease, let me do this part. You have Na2O. The first step is identify the metal and non-metal. Sodium is the metal and oxygen is the non-metal. So your ions are Na positive. How many? 2. And oxide ion or oxygen anion 1, 2, 3, 4, 5, 6, 7, 8 with a negative charge. The second part is MgO, magnesium oxide. Magnesium is the metal, since it will have 2 valence electron. It's going to lose 2 electrons and will develop a 2 positive charge. So one of the ion is magnesium ion. The second is again oxygen with 2 negative charge. So the ions that are present in magnesium oxide are mentioned here. Oh, I'm so sorry, student. Here the charge should be 2 negative. Since oxygen has taken 2 electrons, so should be 2 negative. With this question, I come to the end of this video. In case you like my video, do please spare a moment and give it a thumbs up. In my next video, we'll talk about properties of ionic compound. So stay tuned to my channel, do subscribe to it and share this video with anyone who you feel might benefit. Thanks for watching, and until next time, take care and stay bonded, my dear learners.